the following. I think we should probably be able to do that. That shouldn't be too terrible. So let's warm up tonight with some eigenvalue questions. SPQ, how you doing, my friend? Welcome on in. Okay, so question 2. We don't have a diagonal or triangular matrix. And I'm trying to think, like, we could convert stuff, but I'm not exactly sure how that changes the eigenspace. I think that would change the characteristic equation, right? Like, the only way that I can, actually, if they're similar, but it doesn't matter. I think what chances are, if my students see something like this, they'll probably look at the definition of eigenvalues and try to make that work. I've been like living vicariously through watching it on like YouTube Shorts, and it's just not as good. It's just not as good on YouTube Shorts. So what do we want? We want Ax equals lambda x, or kind of the big idea here is that we need a minus I lambda x to be 0, right? And specifically, we're looking at the determinant of a minus lambda I. I guess I can write this in a better order. So if we can find a minus lambda I, find that determinant, we can probably make some conclusions about the determinant, right? So we know that 0 is always going to be a trivial solution, but we're looking for non-trivial solutions, and that should happen when the determinant is equal to 0. So let's find a minus lambda I first. So 2 minus lambda, we're going to have 0, 4, 0, 3 minus lambda, 0, 0, 1, and 2 minus lambda. And we should be able to go right into the determinant relatively quickly. Do I want to move some stuff around? I mean, I could do a little, no, I don't want to do a row swap. I was like, maybe I could do a row swap. But anyway, let's grab green. And we'll write out our other columns here so we can do a quick little weave method for the determinant. So the determinant of a minus lambda I should be equal to, we're just going to multiply it right across our main diagonal. I know I love eigenvalue things. They're so cool. And then we have an addition of 0 and then an addition of 0. For our 3 subtractions, we should have 4. So we have a subtraction of 0 here, a subtraction. Really? I guess it was just triangular enough. Yeah, that's crazy. So we get a 0, and another 0. So that's super nice. And let's just double check. The only positive term I get is this one, and I get 0 everywhere else. Perfect. Okay, so I'm happy with that. So that means that our determinant is actually already completely in factored form. That's super nice. So we have 2 eigenvalues. We're going to set this equal to 0 and solve that. We get lambda is equal to 2 and lambda is equal to 3. So 2 eigenvalues. One of them happens to be a repeated eigenvalue. So let's, I guess, now check in on finding the eigenspace for each of these eigenvalues. So we should be able to find, hopefully, basis vectors that correspond with each one of these eigenvalues. And the basis vectors that we find should help us determine what that eigenspace will look like. So let's look at the eigenspace for, let's say, lambda equals to 2 first. So let's go back to our matrix, which is A minus lambda I. And instead of lambda, we're just going to input the number 2. So let me see. We have, so 2 minus 2, 0, 4, 0, 3 minus 2, which is 1, 0, 0, 1, and then 2 minus 2 is 0. Okay, so if we were to make a substitution, lambda equals 2 in, we should get a matrix that looks like this. All right, so we have 0, 1, 0, 0. So this should be our reduced row echelon form. So we have rank 2. And, right, that should work. That should work, yeah. And so we now need to consider this matrix times x is 0, right? I always kind of forget how to do the final little bit. Or the other one is we need a... How do I do? I think I do it like this. I think I consider like 0, 1, 0, 0, 0, 1, 0, 0, 0. And I take some random vector x, y, z. And I need this to equal the 0 vector. So I know that x equals 0, y equals 0, and z is going to be a free variable. So I think that's how we do this one. So x equals 0, y equals 0. And the last thing that we would get is that z is free, right? So this row corresponding to the... Or wait a second, is that right? No, I lied. Let's actually do this multiplication. So when I do this multiplication, I'm going to get 0 plus y plus 0. And then I'll get 0 plus 0 plus z. And then I just get 0. Oh, interesting. So it turns out that y and z are going to be forced to be 0, and x is actually going to be our free variable. Okay, that makes sense. Okay, happy with that. So that means that our x, y, z should look like t, 0, 0. And I'm going to factor out that t and grab our basis vector. So 1, 0, 0 should be the basis vector that we need for this particular eigenspace. Now, I don't know how we write this. So this is an eigenspace. Let's just call it capital E. This is the one corresponding to lambda equals 2. It's going to be the span of this particular vector. Sweet. Okay, let's look at the eigenspace for lambda is equal to 3. So here we need a minus 3i. And we'll have to go back and grab that from our previous matrix up here. So if I substitute lambda equals to 3, we're going to get negative 1 on the corners. Okay, so we're going to get negative 1, 0, 4, 0, 0, 0. So we're going to introduce a 0 row, and then we'll get 0, 1, negative 1. Okay. So I think it's negative 1, 0, 4. We get a full row of zeros, and then 0, 1, negative 1 is going to be the other row that I have here. Perfect. Yes. And now everybody knows that Don has the best beard on Twitch, aside from maybe that one Colossus. What is our reduced row echelon form going to look like? We might need a couple steps here. So let's multiply by minus 1, and let's move our other row up and move our 0 row down. That's probably as good as it gets, to be honest. I don't think I can simplify this much further. So that means that we have this matrix times x, y, z equal to the 0 vector. And if we multiply out the left-hand side, what are we going to get? We're going to get x minus 4z. We will get y minus z, and then we'll just get 0. Okay, so it's up to us to figure out what to do with x minus 4z equals 0 and y minus z is equal to 0. Now, typically in this situation, we introduce an extra parameter, so we're going to set z equal to t, kind of like what we did above when we didn't have something to do with x. So we'll set z equal to t. That means that y is also going to be equal to t. We'll just move this z over to the right-hand side. And then x should be equal to 4t. We'll move the negative 4z over. So x is equal to 4t. And so this means that my eigenvectors are going to look like 4t, t, and t. And if we factor out that parameter, we should get 4, 1, and 1. So we get a single vector here again. So just one free variable, right? One free parameter. But our eigenspace for lambda is equal to 3 should be the span 4, 1, 1. Now what we could do is we could go grab A, and we could go and check and make sure that these particular vectors are indeed the eigenvectors. So if we grab A, because I'm a little nervous that we only have 2 basis vectors. I don't really, I'm just not sure that, I'm not exactly sure what's covered in the class because I don't teach it, right? I'm just the one editing the video. So, but what happens if we take A and we multiply by 4, 1, 1? So let's say we take 2, 0, 4, 0, 3, 0, 0, 1, 2, and I'm even just going to go maybe a little bit more general. Let's just go 4t, t, and t. And let's see where this goes. Has rank 2, so it should be correct. Okay, thanks for the clarification, SPQ. Did it ask me to diagonalize? Oh, it didn't. It just wants the characteristic equation, eigenvalues, eigenspace. Okay, so I didn't have to diagonalize it, so phew. So we're pretty much done after we find the determinant and the trace. But I think it's important here just to kind of go back. Let's double check our work and make sure we're happy with it. So where do these vectors get sent to? They're going to get sent to 8t plus 4t, 3t, and t plus 2t. So if we simplify this, we're going to get 12t, 3t, and 3t. And so what I notice is that as we move from here to here, we've actually multiplied by 3. Right? So 3 represents the I guess, expansion, right? Or kind of like extension of this vector. So this initial vector 4t, t, and t gets multiplied. It gets scaled up by a factor of 3 when we apply it to or do a left-sided multiplication by a. So that's cool. So I think that's the one we just got for lambda equals to 3. So I'm happy with that. That makes sense. So the other one I did want to check was what happens if we take 2, 0, 4, 0, 3, 0, and 0, 1, 2, and we multiply it by, what did we get? We got like t, 0, 0. Okay. So what happens when we multiply this by t, 0, 0? So, oh, I see what's going to happen. We're just going to get like 2t, right? So 2t, yeah, plus 0, and then we don't get any other components. And so I can see that this initial vector, when we do that left-sided multiplication by a, gets scaled up by a factor of 2. So 2 here represents that eigenvalue. So, okay, I'm super comfy with our eigenspaces, super happy with our eigenvalues. So the last thing we need to do to finish off the question is to find the determinant and the trace. What do we got going here? So trace of A should be, I believe, 2 plus 3 plus 2, right? It's just the sum along the main diagonal, so 5, so 7. And the determinant of A is 2 times 3 times 2, so that's 6 times 2, so that's 12. 0, 3, 1, 4, 0, 2. So we get, 12, we get 0, we get 4 times 3 times 2, so 24. And then we do 3 subtractions. We do 4 times 3 times 2, so that's the same thing that I had before, so 24. And then we minus 0, minus 0. So our determinant should be 12. And we can verify our work here. We know that lambda equals 2. It's a double copy of 2, right? We actually had 2 copies of 2. So it usually, from what I remember, is true that the trace should be equal to the addition of our eigenvalues. So 2 plus 2 plus 3, which is 7, right? So that looks good. And then our determinant should be the product of all of our eigenvalues. So 2 times 2 times 3, which is indeed 12. So I feel pretty comfy about those answers. I have a way to kind of double check to know that those look good.